Welcome to the third session of the webinar. Now I shall start the session.
Thanks, Manisha. Good evening, everyone. So I hope my screen and presentation mode and audio is audible.
You're audible, Ayush.
Yeah. So this is third session in the series of LLM development sessions that we have started. And as previously, we are putting all the materials onto this GitHub repository. And today we are going to, so in previous two sessions, we covered how to understand the hardware performance, both in terms of communication, computation, and as well as real world performance. Then in the second session, we looked at various aspects of data curation. So there is different components, pipelines. The complete pipeline has different components, which helps us in creating clean data to train the LLMs. And this has aspects with respect to how we are going to run those very large raw data on either to parallelize them and run them quickly so that you can start your do not spend too much time on cleaning the data with respect to the computation and can start on the training part. So today we are going to cover this. How do we do large scale LLM training in a distributed manner? So assuming that we have a large cluster of GPUs which have different nodes. So each node can contain either 2, 4, or 8 GPUs, and now we have several nodes of them. Now, how do we scale our training such that we can extract the maximum leverage out of the underlying GPU architectures? So, yeah, so the agenda looks like this. We are going to cover different concepts related to parallelism. So when we are going to start our training, how do we ensure that our model parameters, gradients, and different optimizer components are properly split up so that we can sync them together properly after each step of training, and then we can do gathering, do a reduce operation such that our training is in sync and goes in a appropriate in a stable manner. And how do we combine all of these different parallelism to work together, both in terms of visualization and intuition that we are going to understand. And thirdly, mixed precision training. So today we are not going to cover the transformer architecture because this is one session that we have of 1.5 hours in which we have to cover one demonstration as well. So we are not going to cover in the transformer architecture. How does this help in training LLMs, in generating useful content that we are now seeing through various applications. And also we are not going to cover the latest part of FP8 training. So as if the situation demands, we can cover it later point of time, all these things. But today we are going to focus on these three things which are important from the perspective of training LLMs in a distributed manner. So yeah, let's start with basics. So how do we train a neural network on a single GPU? So this is basic concepts of reading the data, then transporting the data from CPU to GPU. So for example, if we are doing any loading operation, data loading operation using NumPy, using pandas, popularly data frame or NumPy, then we load them either using on the GPU and then on CPU, and then from CPU it is going to transfer on GPUs. But now there are several libraries that we discussed previously as well, like Rapids, which allow us to load the data directly to GPUs, skipping the step of transferring the data from CPU to GPU. And then we do data loading or cleaning the data, and then we transport the data to the GPU. So here, we know neural networks are basically an optimization problem that we are trying to solve. And they are complex functions because there are a lot of parameters that needs to be learned optimally. And there is a non-linearity with respect to the activation function. So this optimization function is not convex. It's highly non-convex. So the solution is not tractable by hand, or it can not be computed directly. So even though it's non-convex, still they converge. So it's not clear why they converge, but they converge. And using simple stochastic gradient descent kind of algorithm, we are able to converge this highly non-convex function and reduce the loss. So now, how does this stochastic gradient descent works? Briefly, we calculate activations, which introduces nonlinearity for each layer, and then calculate the output, then calculate the loss, and then backpropagate this loss, what we have got from the last layer. After the last layer, we are going to do a derivative with respect to each parameter and calculate how much each parameter should be updated in the right direction, assuming that we do not fall into a local minima. So most critically in this whole process, there are two steps which takes most of the time or matrix multiplication. One is this calculating the activations and output, step 6 to 8, and then 10 to 12, which is backpropagating through each layer. So yeah, this is completely how does it happen on a single GPU. Now let us, so updating the weights, returning the control and so on. So that's the logistical part. Now let's see how does it happen on multiple GPUs. Because in this particular session, we are most concerned about how does training happens on multiple GPUs or multiple nodes. What does different communication protocols, what are the challenges that we see in terms of, different kind of, or setting up a very large model on a single node or multiple nodes. So those we are going to see. So that's why this motivation is with respect to how do we train neural network with multiple GPUs. Now with multiple GPU, again, we know the critical operation is the gradient all reduce that we saw in step 13 previously. So essentially, when you are training with a neural network which can fit on a single GPU, then you are just going to create a copy of the complete model and put them into different GPUs. Now here, understandably, when you are going to do a backpropagation step, you need to ensure that your gradients, or even during the forward step, you want to ensure that at the last layer, your losses are averaged or they are in sync with each other, such that both the GPU contain the similar copies of the parameters or the gradients. Right? So this is a critical step, like assuming like your model can fit on a single GPU. Then we have to do a lot of communication with respect to passing of gradients, passing of parameters from one model to another model, which is on different GPUs. So this collective communication becomes the kind of bottleneck when we are going to scale our whole model. So the key takeaway from this slide is that as communication scales with respect to model size, while computation scales with respect to model size and batch size per GPU. So as we add GPUs, computation per GPU will remain constant, but communication overhead will change. Right? Yeah, this is a very simple setup where we do like distributed data parallel. The expansion of this DDP is distributed data parallel, where we are going to keep different copies. So again, this is again a similar representation. Now, if you could remember in our first session, we discussed about different communication primitives within the GPUs. So we discussed about reduce scatter, all gather operation, and then all reduce operation, all to all operation, which forms a very foundation block of the of training any kind of model, because there's supposed to be a communication if your things are not fitted within a single GPU, and that is mostly the case. So here, that's why this gradient passing from one GPU to another to ensure that all the gradients are in sync as a reduced scatter operation that happens. And this is part of the nickel NCCL library that we discussed in the first session. Like that's why it forms a very basic foundation of the working with the GPUs. So yeah, so that's why like first session covered most of those things with respect to the communication, computation, and so on. Yeah. Now coming to the topic of distributed training. So this is more from the context of larger models, because if we have a very small model or very few parameter model, and whose copies do not need to be created, that can be run very quickly on a single GPU, even with enough amount of data, then we don't need to do this distributed training. This demand only comes when we are going to train these large language models, may it be for the pre-training or maybe for fine-tuning. If your model is very large, let's say if it's a deep seek kind of model which has 600 billion parameters, which cannot fit on even a single node having of H100. So H100 has 80 GB memory, and 8 of them on a single node constitutes like 640 GB of memory. So with a some precision, assuming like it's a 16-bit precision, it cannot fit within for fine-tuning even within a single node. So that's why we need to understand this part, like how does communication with respect to both the hardware layer, which we covered in session 1, and now from the software perspective, how does it maintain different copies, or how does it do this complete logistics things to ensure that the training happens in a stable manner when we are doing some distributed training. So some overview of the this parallelism that we call. One is the distributed data parallelism that we just discussed. Like you keep n copies of model parameters. So assuming your model is small enough to fit into a single GPU, then whatever GPUs you have, you create n copies of that, and whatever batch size you are going to feed for a training, you divide that by n, so that each copy will have batch size divided by n number of instances that goes for each instance. And now after each, while you're doing a forward pass on the model, then after the forward pass, you do averaging of all the parameters, because your activation, not parameters. Your activations you need to keep track of, because when you're going to backpropagate, your activations are going to come as a derivative in the chain multiplication during backpropagation. So that's how you do this communication operation frequently when you are going to do this data parallelism kind of effort. Now, secondly, when your GPU is not going to fit, when a model is not going to fit within a GPU, then when we go with the concept of model parallelism. So there we have majorly two kind of model parallelism. One is Tensor MP, and second is pipeline model parallelism. So here we maintain a single copy of model parameters because we don't have enough. The concept is you split the tensor, or the layer on different GPUs. So here, if you see, tensor model parallelism splits the layers within layers of the model onto different GPUs. So one GPU will contain one part of layer 1, and another GPU will contain another part of layer 1. Now in pipeline, what happens is, so let's say if your model consists of 2 layers, then layer 1 will be residing on GPU 1, and layer 2 will reside on GPU 2. So both the operation, the GPU 2, let's say is having layer 2. So then to do any computation for layer 2, it needs to wait for layer 1 to finish. Unlike in tensor parallelism, tensor MP, you do not wait for layer to finish. Both the operations need to be, because you are splitting the layer 1 into 2 parts, your metrics into 2 parts. Now, so you need to do some operations to achieve. You need to do so much communication between each other in this tensor parallelism, is that it becomes prohibitive beyond certain number of splits that you can probably do. So we are going to look deeply into both these parts, data parallelism and model parallelism, later point. But yeah, this is more or less the broader thing. So yeah, as I mentioned, data parallelism is the model copy on each GPU, and at the end of every iteration, you do reduction of weight gradients. So essentially, basically these gradients, you probably know the concept of like how does these gradients are being calculated. It's just a derivative of a parameter with respect to the loss. So now, after each iteration, because each model copy has seen different parts of the data, so it will have different values with respect to the gradient, because your parameters and loss are updated differently. So at the end of each iteration, you generally you generally average the gradients of whatever model copies that you have across all the data parallelism data parallelism value, and then you are going to propagate or broadcast the average value to all the model copies, such that all the model copies are in sync with each other. Yeah, so this is popularly implemented, and there is a simple wrapper by which, or now it's just a matter of simple argument that you need to just to pass, like how you're, if you're going to use this BDP wrapper or not. So yeah, this is the high level abstraction of this. So as I mentioned, you do a forward pass, and with respect to activations, you are mostly concerned because parameters are again different on different GPUs. You calculate the error, then you do a backward pass, calculate gradients. So for the same number of parameters for each copy, you calculate gradient separately. And now you are going to do a reduce scatter operation. So what does this mean is, in reduced scatter, each there is a there is a averaging operation or a sum operation that happens for all the GPUs that are there with in your data parallelism value, and then each source. So because you are mostly concerned about like you should get the average or you should get the result from the GPU2. So GPU1 is concerned like what is the gradients for those number of parameters. So GPU1 is mostly concerned about that, and then it updates its network weights. So because you need gradients to update the optimizer to update the weight. So that's why you update the weights from the available local part of the gradient weights. And once that is done, you do an all-gather operation. That means you broadcast your gradient to all the other GPUs, which such that all the GPUs can see all the gradients from different n-1 models, and then it does an averaging operation here. So this averaging operation happens to syncs the gradients across all the GPUs. Right? So these are like different batches. You do a splitting of the incoming batch. So essentially, it reduces your time by n times, because if you would have a single GPU on which you would be training, now you have n number of GPUs on which you are training, and you are going to split each batch separately. There is no overlap with respect to between batches. So you are going to reduce the training time by n times. Right. Now, this distributed data parallel has a, I think, yeah, I'll just go through this slide, because to just get an assessment of how much GPU memory is needed to when we are going to train a complete network. So the network consists of model weights, as we know, and they are mostly in 4 bytes or 2 bytes, depending on the user choice. And then, in order to ensure that our model is trained properly, we need to keep track of the optimizer states. So optimizer states consist of like different algorithms, like SGD do not keep track of previous optimizer state. So you do not need to store it for each parameter. But most popular algorithms like AdamW needs to keep track of the parameter state of the previous iteration or previous step. So for each parameter, you need 4 bytes for maintaining or for storing one state, and 4 bytes for maintaining another state. So basically, these are variance and momentums. So these are two states that you probably need to store out for each parameter are moments and variance. We are not going to get into detail because that will take quite a bit of time. So again, you need 8 bytes into number of parameters within a model for storing the optimizer. And then for gradients, you again need it because when you are going to update the weights, you need the you are going to keep the what is the gradient with respect to loss for the particular parameters. So gradient is again stored in 4 bytes. So 4 bytes into number of parameters. And again, you need activations to be stored. So now, why is this important? Because activations, again, it features within the whole backward propagation where you need to multiply, where you do a chain kind of calculations, multiplications to update your weights or to find the gradients. So activations depends on several factors. The key factors are the sequence length, hidden size, and batch size. So for long context training, activations often dominate total memory consumption. So that's why we have another kind of parallelism for long context training. But essentially, if you can sum all of them, so 4 plus 8 plus 4, it comes out to be 16, but roughly it is like you need 18 bytes per parameter just for for all these gradients, optimizer state, activations, and so on. So 18 to 20. So essentially, if you're going to train so if you're going to train, let's say, 340 billion parameter model, then you multiply 18, the number of parameters by 18, which comes out to be 6120 GB. So this much GPU RAM is required to store the single copy of the model while training. So 6 GB of the memory. And if it's a smaller model, let's say 8 billion parameter model, so you need like 18 into 8, which comes out to be around like 150, right? 144, 150. So you need that much GB RAM in the GPU to store all the parameter states or optimizer states. So to prevent this overflowing requirement of huge memory, that's why different kind of parallelism are proposed. Data parallelism, as I mentioned, is one of that, which does not is only applicable when you have a smaller model, but it is used in combination with other model parallelism. Now coming to another modification of a distributed data parallel, which we call it FSDP, which is fully sharded data parallel. So as I mentioned, alluded here, the optimizer states, the gradients, activations store the large amount of memory. They need the largest amount of memory. So the idea in fully sharded data parallel is, can we reduce the memory requirement by partitioning the model state across GPUs? So instead of doing all reducing gradients, we use reduce scatter to distribute gradient accumulation. And essentially, I'll just take this. Yeah. So here, if you see, there is one type of FSDP. So here you have a GPU which contains parameters, gradients, and optimizer states. So as I mentioned, optimizer state is like 8 bytes, so that constitutes the biggest chunk of the whole GPU memory requirement. Now the idea in the FSDP is, can we shard the optimizer states? So can we shard the optimizer states across different GPU ranks? So immediately it cuts the memory by roughly 8 bytes per parameter, assuming you have like eight GPUs. So this will reduce the requirement of memory that needs to be available within a single GPU. Because you are not going to only shard or only keep the optimizer state, for the assigned. I mean, you are going to divide the optimizer state into n number of chunks, and then you are going to only hold a copy of that optimizer chunk on the particular GPU, right? So this is like one part, and then this is like stage one. And there are like different stages. So first is the optimizer state, and this immediately saves like 8 bytes per parameter with the smaller amount of complexity of implementation. Now in stage two, what we do is, instead of reducing just the optimizer states, we do the reduction of gradients as well. So here, if you see, the gradients are also now distributed or sharded on different GPU ranks. And now in the zero stage 3, in addition to parameters and gradients and optimizer state, you also shard the parameters. So now you can assume, like, if you are going to do a one training round of data parallelism using this strategy or one training step, then you need to, when you are done with one part of the optimizer state, then you need to copy the optimizer state from a different GPU, and or maybe a CPU, and then you are going to compute them and then discard them. Before discarding, you need to also pass the message to all the other GPUs that this is the latest, the latest values of the optimizers. So again, you need to do a lot of computation. But if these computations are within a single node or within a GPU or GPU to CPU, then the communication is still manageable. So you probably will not get lot of you can probably hold the, or train your model, very large model, on a smaller single GPU without sacrificing much of the, because otherwise you would not have been able to train the model at all. So as a consequence of this kind of sharding of optimizer states, gradients, and parameters, now you are able to, you are able to at least train the model, and the only bottleneck that could come from the forward pass and backward pass would be one operation, one collective operation, which is all gather, because you are essentially doing the all gather parameters for each layer, compute, and then discard the immediate shard that you have just copied. And during backward pass also, you are going to all gather the parameters again for gradient computation, and then propagate or reduce scatter the gradients to other ranks, other GPUs. So this allows you to, the only bottleneck could come from the communication point of view. Otherwise, you are able to manage this mostly from the implementation perspective as well, quite stably or properly. Yeah, so this we already covered. So yeah, now coming to the model parallelism part. So just to recap, we covered two parts in data parallelism. One is data parallelism, where each model contains, each GPU contain model replica. So all the GPUs contain each individual model replica. And fully sharded data parallelism, where we shard the optimizer states, gradients, and parameters, which constitutes the most most GPU memory intensive or GPU memory heavy operations, heavy operations. So that is two components that we covered. Now in tensor parallelism, we partition individual layers across GPUs. So as I mentioned, probably we'll go to this. Yeah. So in tensor parallelism, we are going to split one large model across GPUs and sharing layers or embeddings across GPUs to all run at the same time. So let's say my layer, I have a 5-layer or 6-layer of model architecture. Then I'm going to split. If my tensor parallelism is set to 2, then I'm going to put 0 first and second layer on GPU 1 and third, fourth, and fifth layer on GPU 2. So here each GPU will process, and the other part of the GPU, the other GPU which has the later part of the layers, will wait for the model to complete the operation. And also there is like, if we are going to do any backward pass on top of this kind of scenario, then we need to do a lot of communication, because for each layer you are going to transfer the the parameters and gradients back to another GPU. So there is a lot of inter-GPU communication that happens, right? And in pipeline parallelism, let's say if you have, I think I said it reverse. I was mentioning about the pipeline parallelism initially. So this one is pipeline parallelism. Okay, I'll repeat. So, and pipeline tensor parallelism again is this large model split by across GPUs, and layers and embeddings are shared across GPUs to enable them to run at the same time. Unlike in pipeline parallelism, where each layer, depending on the value that you have set, let's say 6 layers and there are 2 is the pipeline parallelism, then 3 layers are going to reside on the GPU 1 and 3 layers are going to reside on GPU 2. Now, for tensor parallelism, understandably, we are going to see like how there's a lot of communication that happens, that needs to happen from one GPU to another GPU. So tensor parallelism are generally set within a server. So we do not want the communication to happen through copper wires or via InfiniBand or some other protocol. So we use this tensor parallelism such that the layers are cut and stay within a GPU, within a node. So they do not split across nodes. And pipeline parallelism generally is that they can be partitioned across servers or across nodes. So by combining these two types of model parallelism, we can scale the model to trillions of parameters, and and we get a lot of throughput improvement also, like in terms of different kind of parallelism that we apply. So if we set the value from, let's say, tensor parallelism to a smaller 2, 4, or 8, because we are going to again set this value within a node, not across a node. And so we essentially get like with different values of tensor and pipeline parallelism, we get like different throughput improvement. Now let's get into the depth of tensor parallelism. So this particular parallelism is actually well suited for transformer architecture, because transformer is kind of a kind of architecture which is dominated by large matrix multiplication, right? So it has like attention, in the attention layer, there are query, key, and value, where the list from with respect to the input, there is a lot of multiplication that happens with those large Q, K, V matrices, and again with the MLP layers, which are again very large. So these operations can be partitioned across GPU while maintaining large. They can be partitioned across GPUs. And secondly, the attention and these MLP layers have regular communication requirements. So what happens is there is typically, we are going to see like there's typically one all reduce per layer in forward and backward pass, and this enables like tensor parallelism because for each parameter or for each parameter you're going to do a backward forward pass very quickly. So we do not want them to travel through like intranode. So that's why we keep it within a node. So NVIDIA DGX servers with NVSIPs has 800 as 600 gigabytes per second GPU to GPU bidirectional bandwidth. So this is particularly suitable for the tensor parallelism kind of operation. For H100, it's 900 gigabytes per second, and for B200s, this is 1.8 terabytes per second. So GPU to GPU bidirectional bandwidth. Yeah, so this is transformer cell. We have an input, then we have a position embedding. After dropout, we have a attention layer where we have different operations that happens. There is a multiplication of the input with the query weights, key weights, and value weights, and then these queries and keys, again, the transform matrices are again going to be multiplied together to apply softmax operation along with the computation of the weights or the values that needs to be there for the each token or the embedding. And then there is a MLP layer where the downscaling and upscaling happens. And these are again operations that can be split across GPUs. Yeah, now coming to the details part, like how these are going to be split across GPUs. So let's say there is a ReLU operations or GeLU operations. So ReLU is just an activation function which quashes the input between 0 and the value of the input. So it's a minimum of 0 to 0, x. So now there are two approaches where you can split the incoming input x either column wise or row wise. So let's say your x has an input which is now split into x1 and x2, and now your a, which is a row wise implementation that you need to do, is again split into a1 and a2. So again, this is a matrix multiplication, and you can do this operation like x1 into a1 plus x2 into a2, and then you apply the GeLU operation. So this is like when you split the x column wise and the a row wise. So a are again these parameters or activations. So before GeLU, we need a communication point because x1 a1 and x2 a2 needs to be summed together. Now in approach 2, where we split the a column wise. So instead of doing split row wise of a splitting, we do a column wise splitting of a. Now XA produces these two operations like column wise XA1, XA2. So we don't split the X here. Right? So you keep a X, you do a multiplication XA1, XA2, and now because you split the column wise, then you just do at the end a concatenation operation. So this GeLU can be applied independently to each shard. And we defer the synchronization for the later point of time. So here, if you see, GeLU is applied element-wise. We know like GeLU is applied element-wise because after the multiplication, we do the max of min of 0x and so on. Max of 0, so max of 0 or x, 0 x if it's negative. So now here GeLU is applied element-wise, so it can be computed independently on each shard. So that's why this tensor parallelism, the splitting of column-wise is more superior, because now in this case you can compute do the GeLU operation independently on each shard, And we can avoid this pre-GALO synchronization that we do like here, like summing of this operation. And this reduces the communication frequency, right? This is how it happens, and this becomes a chosen approach because now you can do operations independently. Then there is less communication that needs to happen. Yeah. So now with a column parallel, each GPU computes GALU. This is just a repeat. I just want to highlight. So let's say your layer is now split across two GPUs. So you, for a given input, you split the A, and then you do the operations to apply the GALU operation and so on. And then you compute some Y1 and Y2, the output of this GALU operation. And then you just do the rest of the operations like here. Yeah, rest of the operations after GALU, you do a dropout. So you can do it independently on each of them. So before dropout, you need to, you need to concatenate both of them together. So again, you need to do some communication here because each GPU should now contain the information that is not on their GPU. So there's going to be a communication of the final Z1 and Z2 to each other GPUs. So there is some all reduce operation that needs to happen. And then you apply the dropout over the collective concatenated output, right? So this dropout operation again, in contrast to the column parallel partitioning that we saw for the A matrix, right? Here we are doing the row parallel partition, if you see here. So here, the forward pass requires an all reduce. So we can sum the contributions from all chart while the backward pass is identity. So if you can think about the dropout operation, there is during the back propagation, it's just an identity for the cells or for the nodes or for the parameters which are not discarded. So dropout is generally a discard operation with probability P. So it removes certain parameters to be computed for that particular step. So during backward propagation, it's just an identity operation. So that's why we do this row parallel operation here for the dropout part. And this becomes kind of a conjugate. So there is a column parallel GALU operation. Yeah. So there is a column parallel GALU operation for the A1 and A2 that we do. And there's a row parallel dropout operation that we have to do in the dropout case. So these are again kind of a conjugate operation. So and this becomes easier to implement. Right. So F is this for this particular part. This is in the forward pass. This is identity, and all reduce in the backward pass. Because when you're going to do the backward pass, you are again going to compute the parameters, update the parameters with respect to this activation output of this activation function, which is Y1 and Y2. So you need to transmit or broadcast your part of updates to another GPU or to other GPUs in the network. And in the case of this particular dropout operation, the forward pass is all reduce because here after you are going to sum or concatenate Z1 and Z2. So this is an all reduce operation. And then in the backward, it's an identity operation. Right. Now, as you might be getting an intuition now that this is slow across inter-server because there is a lot of communication links that needs to be propagated for each parameter here. And this is not feasible when their communication link is not fast enough. Now, similarly, as we do for the MLP part, we can do for the self-attention part as well. So self-attention, as I mentioned, consists of these three matrices, which are again for the multi-head attention case. These are like different parameters or splitting of these matrices onto different heads. And so there are two main approaches for this. First, this is partition by attention heads. So each GPU handles a subset of heads. So again, this is in the context of the tensor parallelism. And the second approach is like you partition the projections, but gather for attention communication. So you partition the projections in the sense like when you're going to use these projection matrix, multiply them by the input, you partition those projections and then do a all-gather operation when you're doing the computation for attention. But this head parallel approach is generally preferred because attention heads are independent and the computation requirements or communication requirements are more predictable, right? So when we are going to decide our tensor parallel size, we need to be cognizant of the fact that the number of heads in our architecture or in our model is divisible by the tensor parallel size. So let's say if you are going to set your one number of heads as 12 and your tensor parallel size is 8, then the division comes out to be like 1.5. So which is not possible to fit, which is not recommended to fit half head onto one GPU and another half into another GPU, which increases the communication requirement during forward and backward pass. So yeah, this is how you can do tensor partitioning for self-attention part. So yeah, so in summary, there are two things that we discussed. One is the self-attention part. There are two all-reduce operations that happens both in the forward and backward pass. And in the model parallel case for the NLP layer of the transformer, we again do the two all-reduce operations for the GALU and the dropout. Yeah, that was about the tensor parallelism. Now we will discuss about like pipeline parallelism. So let's say assume like there are 4 pipeline stages where each stage is processing one batch. So as I mentioned here, so now your complete model is now split into different layers. So each layer is yeah. So now there are like 4. So for a single batch, you have split your complete model into different pipelines. So here your one batch is going to be processed on one GPU, another batch is going to another GPU, and so on. So there are, until we have like 4 stages which are finished before we can proceed the after that we have to proceed with the backward pass, completion of the backward pass of the the lastmost layer here, because we are going to do backward from the front from the finish again. So the fundamental issue here is this batch processing creates dependencies. So we need to do this serialization of these pipeline stages, and without doing any special things, this GPU utilization can drop to like 25% or lower, because there is a lot of bubbles, or there is no processing for this much amount of time until there is some backward pass related to this particular GPU is happens. So there is like a lot of GPU bubbles which do not efficiently use the GPU properly are staying here. So now what is the solution? So solution is particularly so this is it. So solution is to split this batch into micro batches. We'll see like how this micro batching solves the problem. So with one micro batch, there is large bubbles, right? And with 2 micro batches, these bubbles might shrink. And with 4 micro batches, yeah. So this is it. So with 4 micro batches, this bubbles again shrink again, right? So we have like less number of bubbles or pipeline bubbles that are there for the GPU, each GPU. Yeah. So this is the animation, right? You process the 1 micro batch here, and after that forward pass of 1 micro batch, you go into the another micro batch, and then you go to the another micro batch. So here now you have less empty time for the GPU. And once you are done with the forward pass for the 1 micro batch, 1A, let's say, then you do a backward propagation, back propagation for each part. So like, as I mentioned, it's going to be in reverse now. So you do a back propagation for this part, and then you do transmit your collective gradients now to another GPU, and then you do this operation for this part, and then so on. So again, as you split these into more number of micro batches, you are again going to receive less number of these GPU emptiness or pipeline bubbles in the whole process, and so on, right? Yeah. So now here layers are, as I mentioned, are sharded over GPU. Each GPU is responsible for a subset of layers. So unlike tensor parallelism, where we split the matrix itself, within the layer itself, we split the matrix on different GPUs. This is, we are not going to split within a layer. Across layers, we are going to split across GPUs. Each batch split, as I mentioned, is split into smaller micro batches. So when you are going to do any pre-training or fine-tuning, you are going to see this micro batch argument, which helps in this pipeline parallelism. And then, as I mentioned, because now you have these many GPUs with you, so now you need to communicate. Once your backward pass is finished, you need to communicate this information to another GPU so that it can do the backward operation for that particular part. Yeah. Yeah. So again, this is again a small minor modification of the pipeline parallelism, which is interleave scheduling. So here, for example, let's say device 0 or device 1 handles stages 1 and 3, and device yeah. So here, so for this particular thing, what happens is, so device 1, GPU 1, this is going to handle this 1, 2, 3, 4. And again, you do not wait for the backward pass to finish for this particular micro batch, the initial, let's say, micro batch 1. You start processing the forward pass for the another set of micro batches. So the benefit of this is there are smaller pipeline bubbles here and better GPU utilization. And when to use this, because when you have large clusters where network bandwidth is abundant, so there is no congestion of the network, and the bubble cost of, because you want to leverage the GPUs optimally, the cost is prohibitive. So if you not use the GPUs, then the cost is like pretty high. So in those cases, you use this kind of interleave pipeline parallelism. And this is most effective when you have very large models. So let's say if your model has like 50 plus or 60 plus layers. So we repeat those layers in transformer decoder architecture, right? Each block is repeated across different time across the whole architecture, across the whole model to to build your whole architecture, right? So this is helpful when you have large number of layers, large model sizes there, and you can do this kind of parallelism to reduce the GPU bubbles. Yeah. Yeah, as I mentioned, like in this case, you are going to split into micro batches, and then you are going to start doing this interleaving scheduling so that you do not wait for your backward pass for your micro batch to finish to do the forward pass again, right? So this helps you in doing the proper communication. Yeah. Now let's see how does these all model parallelism work together in sync. So let's say you have two nodes. Each node has 8 GPUs, and these are like the values for data parallel, pipeline parallel, and tensor parallel that you have set. Now let's say you have your model which consists of 8 layers. Okay. So there is this model 0, and there's a copy of the model which is model 1. Now this data parallelism. So now to start with tensor parallelism, as I mentioned, tensor parallelism generally we recommend to do it within a node. So your tensor parallel size is 2. That means your 2 GPUs will contain a split of your layers, right? So you have this tensor parallel group 1, group 2, group 3, group 4. So you have 8 groups of tensor parallelism across these 2 nodes, right? And now for pipeline parallel, you have set the value as 4. So now what happens is the pipeline parallel is going to happen across 4 GPUs. So your layers are going to split across 4 GPUs. So now you have like 4 pipeline parallel group for each model copy that you have. And now you're going to do the data parallel across this whole complete two nodes. So what happens is there is a tensor parallel, there's a pipeline parallel, and there's a data parallel group. So when you're going to multiply, so the idea is initially when you are going to multiply all these values, you should get the number of GPUs within your network. So if you do this multiplication 2 into 4 into 2, it comes out to be 16. Now if you could set the pipeline parallel as 2, 4. So it completely depends on what is the model size that you have and how many splits is it effective. How many splits you should do so that it is do the maximum GPU utilization. So that is the overall idea. So if your model is not very large enough, so you set pipeline parallel as 1 and tensor parallel as 1, and then you can do the data parallel as 16. So you can have 16 copies of your model, right? So this is kind of a very rough visualization of all these three parallelism strategies. You do the tensor parallelism, which is a fine grain. Then you do a pipeline parallel, which is lesser fine grained with respect to tensor parallelism because you are going to split the layers. And then you do the data parallel where there is a model copies. So now if you see here, there are two model copies. So let's say if your model parameters are, let's say 50 billion or 70 billion parameter model. So now this 70 billion parameter model is going to occupy this 8 GPUs, where within this 8 GPUs, you are going to have two model parallel groups, pipeline parallel groups. And there is, for 2 GPUs, you have a tensor parallel group. Right. Now let's come to the part of precision training. So there are again different other kind of parallelism that we are not going to cover today because of limited time that we have. So there is like sequence parallelism or context parallelism. So let's say if you have a long context training, so nowadays we have models which can see the context of 1 million or 4 million also, right? So when you have such a large context, your activation memory shoots up. So in the context parallelism, you split your sequences across GPUs. So that is kind of a context parallelism. And that comes up with a communication overhead because you want your model to be trained in a minimum amount of time. So you need to have some overhead communication that comes with the context parallelism. But yeah, again, the best thing is like we can actually train the GPUs with such large, train models with on GPUs with such large context size. So that's again context parallelism. That's again a slight modification of what model parallelism that we have seen. But we are not going to cover because of limited amount of time. So now let's come to the mixed precision training, which is very essential part for large training a large model with respect to efficiency and stability. So why do we use mixed precision training, particularly because there is huge benefit with respect to when we use less number of bits to store more information. So with lower precision formats, weights and tensors can take up like less space in memory, which means we can fit larger models on the same hardware. And because of this, data also moves faster between memory and compute cores, thus boosting our bandwidth, right? Because if we have less amount of bits to store per parameter, then we have less amount of multiplication that we have to do, and then we can do less amount of data movement from GPU to because we saw that like, a lot of communication happens. So this is a typical way to store information in computers. Like FP16 has like 16 bits, where 1 bit is reserved for sign, the 7 bits are stored, 6 bits are stored for, sorry, there are 5 bits for exponent. In Mantissa, which is precision, there are rest of the bits used for 10 bits used for Mantissa. And then there is a modification of this FP16, which is BF16, where we increase the dynamic range, that is exponent, and reduce the precision storage bits. And on top of BF16 and FP16, we have FP32, where you have a larger dynamic range and larger precision to store information. And now there are like FP8 trainings models that can support FP8 that are trained with these FP8 parameters. That is, there are like 4 bits for exponent and 3 bits for precision, mantissa. And there is like modification of again FP8 where there are 5 bits reserved for exponent and 2 bits reserved for mantissa. Right. So essentially, people are trying for lesser bits because you have a smaller model which can fit during inference, and your inference would become very fast. So now different parts of the network like weights, activations, and gradients are affected differently due to these different precisions. So here you see that weights and gradients have different distribution weights. So if you are, let's say, as we move from FP32 to BF16 or FP4, the representable range changes dramatically. Because gradients have here if you see the gradients have the widest distribution. So they are most at risk of being clipped when we are going to move from, from FP32 or BF16 to FP4. So this is just a representation in terms of like what actually the distribution widths of different components of the network. Weights are relatively narrow distribution, so they are, even if you do quantization, they will be pretty stable. Activations have moderate distributions, and if you do proper scaling, keep a complete log of like what activations are scaled, need to be scaled down. They are still manageable, but gradients have very wide distribution, and they are like highly susceptible, because one of the errors that we see, common errors during training the neural network, apart from out of memory, is the NaN errors, right? It's your gradients are not a number, so that's the most irritating and non-debuggable error. So it's because of the underflowing or overflowing of the gradients that we generally encounter these kind of errors. So during quantization, this gradient becomes very vulnerable due to this quantization. And that's why the FP8 trainings or FP4 trainings are generally not, you cannot just run the training and expect it to run, because they're not very stable. So you need to do proper monitoring, ensuring you do not see this underflowing or overflowing frequently. You need to restart your process from that point of time wherever there's underflowing and overflow. And yeah, so why do we need these scaling factors now? Because now we are motivating in terms of like, if there is clipping off due to the quantization, then we need this kind of scaling factors when working with these low precision formats. This represents the distribution of tensor values, and these shaded regions show values could either underflow or overflow if they fall outside this representable range. So without proper scaling, we lose this information at these both extremes. So now you might have understood the fact that the complete precision values are highly useful, because you are going to do these updates in a very sequential, with a very low learning rate. So you want the model to learn very slowly. So if you are going to move to this quantization, then you are going to lose this representable range, or range in which the information would have been stored. So that's why we use scaling. So by adjusting the scaling, we shift the distribution so that as many possible values are fit within this range, minimizing both underflow and overflow. So instead of storing raw values, we additionally store the scale values plus a scale vector. So there are like different ways of storing those scale values. One is like dynamic scaling. Even with respect to dynamic scaling, there are like per tensor scaling or a global scaling factor, so if your scaling factor is fine-grained, then you're going to compute, or you're going to prevent this underflowing and overflowing more properly and get the range of the values, train the model in a stable manner. So so before going into the scaling, I think this how does the automatic mix precision happens with when we train the model would be useful. So what we do, there is a master weight which maintains this parameter copies for parameter updates, for optimizer updates. So we store the weights in SP32 format, and for optimizer states and gradients, we store them in SP32. So what happens is, during forward precision, we cast FP32 to BF16 or FP16 weights. So again, these are parameters which are being casted from FP32 to BF16, and then we cast them back to FP32 for gradient accumulation, right? So here, for each iteration, we do the forward propagation on FP16. As I mentioned, we maintain a primary copy, and then we clip that or cast to FP16. And during backward propagation, we use this FP16 weights, and activation and gradients are stored in generally in FP32 format, because there are more with gradients. They are more susceptible or influenced by the smaller number of weight changes. So if there is like infinity or nan that occurs in the weight gradients, we reduce the scaling factor. So we skip the weight. We could also skip the weight update and move to the next iteration. So all the instances within that batch is now skipped, and we multiply the weight gradient by 1 by S, which is a scaling factor. So on overflow, we reduce scaling factor and skip parameter update. On successful updates, we gradually increase the scaling factor. So this is how the automatic mixed precision, when you are going to train your model, there is an argument like torch.amp or, mixed precision equal to true. So this kind of, with this, the underlying concept is this, that you do a loss computation and scaling with respect to parameters. And this is the complete process of how this mixed precision happens. Right? So you have a model which is in FP16. You maintain a copy of that FP32 because you have cast that. So you need to understand like how much they are scaled. And scaling generally is basically a max function. So whatever max values that you have in your complete tensor, you multiply that to get your scale for that particular tensor. Yeah. So this is about like scaling factors. So here, if you see like for the A100 or Ampere model of GPUs, we have FP16 precision, which is a mixed precision, which has one scale for all tensors. For FP8, we have like one scale per tensor, and we can do FP8 tuning. And for Blackwell, the latest GPU architectures, we have one scale per block of 32 elements. So we see here like how scaling factors have become more fine-grained across GPU generation. Ampere used a higher scaling factor, and now we have like an XFP8 training, which is a micro-scaled FP8 training. So this finer scaling helps preserve more information and accuracy when we use low precision formats, especially for big tensors, which have like very large or diverse values, right? So you keep the scaling. This is the scaling factor that you additionally need to keep track of. Or it is automatically kept track by the GPU feature, the GPU itself. So now you have like smaller number of values. So these are like 32 elements, whose scaling factor is there, and they are like descaled, upscaled, and downscaled based on the the precision training that you are going to do. So now let's take a final look with respect to the matrix multiplication operation that we generally do. That's the most intensive operation that we do within while training a model. So in this MX FP8 recipe, so there are like FP8 recipes, like you have 4 bits for exponent, or 5 bits for exponent, and rest of the bits for mantissa. So now here during the operation, let's say for operand A and operand B here, the hardware multiplies the corresponding scaling factors together. Okay, so it multiplies the scaling factor here with this block of elements, and then performs a dot product on the quantized values, and then applies the combined scale to produce the final output. Right. So here each set of values are associated with per block scaling factors or matrix multiplication accumulates in full precision to avoid overflow. And then output is again re-quantized to the MXFP8 precision with updated scaling factors based on output statistics, right? I hope this makes sense, right? Like you have a scaling factor here, which is for each block of elements, and now you're going to multiply that with the FP8 precision values, these precision values which are in quantized values. So the key takeaway is like we do a accumulation of precision, which determines the numerical accuracy, while storage precision here determines the memory efficiency. And MXFP8 optimizes storage while preserving accumulation accuracy. And now you might be getting an intuition like this becomes very complicated while implementation. So there is like library support with respect to transformer library, not Hugging Face transformer library, but this is again a transformer engine which handles all the scaling of metadata automatically. So you just have to specify the desired precision, and the library manages all the scaling factor updates. As I mentioned, the max value tracking, kernel selection, and so on. So this is how our tensors are quantized in FP8, MXFP8. So here we have an activations that starts in high precision, FP32. They are quantized to FP8, row-wise for activations and column-wise for weights. And the matrix multiplications themselves are again performed in FP8 here for both the forward and backward passes. But the accumulation is done in high precision. By accumulation, what I mean is either the summing or the averaging of all the values, right? So here we do the matrix multiplication, do backward pass here, and we do accumulation here in FP32 because you might be thinking like there are like multiple FP8 values now because we are doing the like per tensor scaling factor of per block of elements, and now you do the aggregation, averaging, or summing operation, then putting them into FP32 block, right? And then from FP32, you are again to cast it back to FP8 for another step of forward pass. So this avoids quantization error from multiple format conversions. Like we are just going from FP8 to FP32. So unlike regular FP8, the transposes of these matrices can't be done in place because block structure changes here. So the idea is like we generate both the regular and transposed, because we need to do a lot of transpose of the matrices, right? So we do this, generate both these regular and transposed tensors, FP8 tensors, directly from FP32, right? So now coming to the implementation part, now there are like various types of scaling factors. There is a current scaling, there is a delayed scaling, there's a block-wise scaling recipe. So for hoppers, kind of 800s or 200s, current scaling is now preferred for better stability, even though it's a bit slower. So the idea in current scaling is we keep the first and last layer of transformer in DF16, which are the most sensitive layers with respect to the kind of information they store. So many people have tried doing the pruning of the last and pruning research. They found that the first and last layer are the most susceptible with respect to the performance of the complete model. So in current scaling, we keep the first and last layer in the same DF16 format. And for the weights and activations, we use E4M3, and for gradients, we use E5M3. And for Blackwell, we have like per block scaling factor for each group of 32 values in a tensor. And this is again a feature of the hardware that helps you in keeping automatic tracking of all the things that happens underlying in the system. Now coming to the libraries part, implementation part, this transformer engine, all these recipes are implemented in this library. It's again an open source library from NVIDIA that allows you to do FP8 training. Two popular frameworks like both PyTorch and JAX. So JAX is again a recent highly efficient framework that is also supported within this transformer engine. And it makes it easy to use like FP8 along with like different types of parallelism. So recently, like QDNN kernels available have operate this grouped gem operation is now also available within this QDNN kernels. So yeah, so this is how like a simple, um, very simple linear neural network FP8 recipe. So yeah, we just define here from the after the import, like we do this MXFP8 block scaling, and then while doing this running the loop, we just do this autocast enable S2 and inform like which is the FP8 recipe, which is the FP8 scaling we have to apply. And that's it, you are done. So there's like all the things are now managed by the underlying library and the hardware, which helps you in doing all these things. And with respect to training of, using the NeMo framework also, so earlier we discussed like NeMo curator. There is also a NeMo framework that we are going to see in like the rest of the 5-10 minutes that we have. It helps you, it also allows you to do this, specifying the argument on which the library, on which kind of methodology that you are going to perform this particular training. So this BF16 with MXFP8 mixed precision is going to be used. So this is how easy now the libraries have enabled it to use the underlying hardware to do the LLM training. So now I'm going to take you through the demo. Let me share my entire screen first. I just want to take you through the NeMo library that allows you to train these models very easily. Yeah, we have, I think, 5-10 minutes now. Yeah. Yeah, so this is the NeMo library, which allows you to do all. So we earlier in the previous session saw the NeMo curator, which is again library for data curation. Now this NeMo library is a complete framework for training the model, fine tuning, do a continuous pre-training, do RL kind of operation for all the for all the modalities like language, multimodal, speech, and so on. So this is a very comprehensive library and it has quite a good support. So it has like around 15,000 stars on GitHub. It does, 18 hours ago it's commit. There was one commit. So there's like highly maintained library and it is provided by NVIDIA. So there is like quite a good support with respect to this. Because this library is again based on the Megatron framework, which is Megatron is another library which is again open source provided by NVIDIA, which helps you to do these kind of parallelism that we have discussed. So again, you might have understood like there's a lot of to and fro operations, all reduce, all gather kind of operations that happens with this this concept of parallelism. So these libraries helps you in masking all the internal details and allows you to just focus on your task with respect to training the model. So yeah, so this is again a very good framework. I just want to show you like how easy is it to train the model, pre-training the model. Yeah, so there are like a lot of LLM recipes that are provided within this complete library. So here, I just want to highlight here like how easy is it to train the model on your data. So pre-training is like very difficult because we need to keep track of like a lot of hyperparameters like these parallelism, learning rates, and so on. So now what this library did is you can just fire this particular command and all the hyperparameters that are mentioned within this Llama 3 8D model is already defined in the Python file. Right, so you do not have to worry about like you are defining some parameter wrong, or there will be some issue that could come a later point of time by just changing some small values. So if you see here, this is the Gamma 2 trainer which was defined, which is defined within this library. So here you see the tensor parallelism is set as one, pipeline as one, uh, and there is like precision as BF16 mix. So all the things that we discussed today with respect to distributed training are like one of the arguments here. And now, with respect to the config, let me go to the Llama. I think Llama 3 would be. Yeah. Yeah, so these are like default configurations. So here you have like the default configurations that was used with respect to like when the Llama 3 model was trained, because it's an open source model. So all the batch sizes, how many number of steps you have to log, your losses, and precision and so on. Do you need to use this FSDP, like data parallel sharding strategy, or not? Right? We discussed about like parallel sharding, data parallel sharding, like optimizer, grads, parameters can be sharded uh, across different across different GPU ranks. All of these are like parameters are predefined here within this library. So you just have to specify your data and you are good to go to run the model, to do the pre-training. And similarly, because most of you might not have the necessary infrastructure to run the pre-training, so there is also like continuous pre-training and fine-tuning notebooks that you can do. Just have to search for it. So this library helps you, provides you this framework to do this fine tuning, continuous pre training. I think there are few examples. Doing that, give me a moment. Here in the tutorials. Let's say here. Yeah, let's say you are going to perform like parameter efficient fine tuning. So there are like Python files that will help you to quickly start and just specify the data and few hyperparameters, and then you are good to go to specify like what is your to do the fine tuning. Like you can do there's like pre-built containers that will help you to quickly start it very easily. Right? That's the benefit of this library. And now I'm going to show you, like, I just run a small pre-training on 8 GPUs that I have. I think they are all like pretty occupied here. So I'll just show you like how did I start with. Yeah. So I just launched a command. I show you that NeMo LLM pre-training command, right? So what it does is it initially starts with some data. So you specify the data on which you want to train. This is again sequence length of 8192 to, as I mentioned, micro batch size of 1, global batch size of 15, 512. So this is again the batch size, which is the sequences, 512 sequences. Each sequence would be having some length, 2048 and so on. And then there are like different configuration. Like as I mentioned, I use this Llama 3 8B. So all the the hyper parameters like optimizer parameters, learning rate, weight decay, and so on are specified here. So once I start this training, uh, yeah. So yeah, I was using like all 8 GPUs here, and there is like a number of parameters. It specified like how much parameters are going to be trained. Yeah, and these are like different bucketing for different parameters. So yeah, like different layers are there. So there are like gradient bucketing. Now here it specified like how many parameters are there within this. So there are like 7.4 billion parameters, out of which all of them would be trained. And total estimated model parameter size is like 29 GB. So I put like tensor parallelism and model parallelism as one here. And once you start this, you will going to receive like, I just started this for 2000 iterations because I do not have much time to do all this. It's just a
Hello.
simple training that, yeah.
Ayush,
Yeah.
sorry to disturb you. Will you please clear which screen you're sharing because you're stuck in that NVIDIA web page, GitHub?
Oh, is it? I shared my
Yes.
complete screen. Okay. Thanks for informing. I'll just share my complete screen. Yeah. Can you see the VS Code now?
Yes.
Yeah. Okay. Cool. Yeah. Yeah. Just want to show you this. Yeah. So here, so the previous GitHub example that I was showing to you, in we just had to start the pre-training by specifying your data. So here I have like once you start launch that command, I started this on Llama 3 8B. So this is a Llama model which uses the Llama 3 8B configuration. So this is the configuration that it has, and I can also change this configuration. Like you don't have to worry about what is the kind of optimizer hyperparameters that it set, what is the learning rate, weight decay, and so on. So you can also run the training on the similar configuration because before starting the actual training, pre-training, you have to verify a lot of things, right? How much is the hardware flops that you are actually receiving? How can if you change the tensor parallelism or model parallelism or the pipeline parallelism or data parallelism, what is the kind of things you are going to, what is the different performance you are going to receive? Like in the distributed data parallel, here I have set like fully sharded distributed parallel as false, I guess. So here, yeah. So here, like uh, I think somewhere here the configuration I have where the fully sharded distributed parallelism is set to false. So I can set it to true as well. And then there is like mixed precision, like what is the precision that I'm using. So Llama 3 was trained on BF16 mixed precision. So it used that, and gradient are reduced in FP32. So all these things are like comes within your package. And how many steps I'm going to train? So like 2000 steps with the with this. Yeah, batch size, the test and validation batch size is this. There is, I think, somewhere it is defined like what is the training batch size. And once you start this process, this is again a pre-training. So similarly for fine-tuning, you will be able to do because pre-training we are focused on parallelism, so that's why I'm showing the pre-training part. So here you see like I'm training on 8 GPUs, and there is like just zoom a bit. Yeah, this is the kind of layers that are defined in Llama 3 8B. I read this. Yeah. And how many parameters there are there to be trained? Like, so there are like 7.4 billion parameters. All of them are to be trained because there's not a FP fine tuning part. And then once you start this, you're going to receive this like what is the kind of loss. You don't see a reduction in loss initially because this is again kind of warm up I'm doing. I have specified warm up step is 2000. And this is just about demonstration. I've just mentioned like what is the just show like how much time does it take to train for single step with a batch size of 512. So there's like 2000 as a sequence length, max sequence length. So if you multiply 2000 by 512, you will get like 1 million as uh, the size tokens. This takes like this much amount of time
Outreach.
in on 8 GPUs. Yeah.
Hello, sorry to disturb you again. Will you please increase the font a little bit?
Yeah.
Thank you.
Is it fine now? Yeah. So yeah, this was like learning rate. This is train loss. So this is complete pre-training. Like you can also export this to weights and biases to see it in the on the web UI and so on. So yeah, this is how it is. I think this is all I have to show now. Yeah. Yeah, I think this is all I have to show. I can go to the questions now. Yeah. Yeah, so there's a question from Aditya. Are there rules of thumb to decide which model parallelism should be implemented, or do engineers test these techniques? So yes, engineers test these techniques, like what is the value of model parallelism to be set or data parallelism to be set for given amount of parameters, model parameters, and these are again available, made available by the community, particularly by NVIDIA. They provide like different hyperparameters for these parallelism size to give you like which will give you the best performance for the given hyperparameters. Yeah. So again, this today's session was more from the distributed training perspective to give you an idea about what is the how do these distributed training happens actually by taking care of different factors. Like there is a lot of communication because when we started with our session one, we focused on communication and computation a lot because this forms the base of all the training, LLM training that we do around. So yeah. On the GitHub again, I'll share the README file which I followed here to run these commands, run these trainings, smaller trainings that you can also replicate in your end. Yeah. I think, Anisha, this is all I have. I think if there are any questions other than this, we'll be happy to take it.
Okay, so we can conclude the session here. Thank you, Ayush. Thank you, Dr. Modani. And thank you, audiences, for joining the session. Thank you.
Thank you.